Hello calculus students, today we're going to look at separable differential equations, and if you're in my class you should have already encountered how to separate variables to solve some equations. So something you might do is, at least with this first one, that's a pretty simple separable equation, go ahead and solve it, find the general solution, and then find the particular solution. Then we're going to look at another equation in context this time in terms of an alternating current circuit, because I know you have a couple problems like that. And why wouldn't we take advantage of the opportunity to learn some interesting features of a complex electrical situation? So you might want to give this differential equation a shot. Let's try to solve that first as well. It's a little bit more interesting. So let's go ahead and look at this one first. So if you remember, the first step in separating a differential equation is to separate the two kinds of variables involved, which at this time, of course, we have x and y. So I'm going to write Newton's notation as Leibniz's notation first, so that I can get this part separated over here with the other x's, and so that I can get this part separated over here with the other y's. Usually we have that as y dy, so that might be a better way to write this one. All right? Next step, class, is to, of course, integrate both sides. All right? So then I'll have what over here? You guys speak up. Y squared over 2, yeah. And then on the right-hand side?
X squared plus c.
X squared plus c. Shouldn't I have a c on this side too?
Yeah, but then you can subtract it to the other side.
The grands.
But this c can be absorbed in terms of that c. Great. That's the implicit. The explicit one's pretty easy to get here, right? So I'm going to call this a temporary constant. The reason I'm going to do that is because I'm going to now multiply it by 2. And so I can just say that 2 temporary constants is this constant. That's always another option that you have to go with. I like the concept of a temporary constant. I could have said like temporary constant 1, temporary constant 2, and then I'd have the final constant. Just an interesting way to subscript things that I think is informative. It's up to you though. The last thing we want to do to get it explicitly is square root both sides, right? Don't forget your plus or minus. So there we go, that's the final constant's going to be living inside the square root this time. So we did have an initial value problem because we had an initial condition. So there's the family of solutions. Which one of those goes through this one in particular? So I'm going to say plugging in 4 equals plus or minus the square root of 2x squared plus x squared. I'm plugging in 0 for x. Plus c, so that's going to be 4 equals plus or minus the square root of
0
c, or 0 plus c, right? So then I can square both sides, and you can see that the plus or minus isn't really an issue here, and c is going to be 16. So my particular solution, that part of the slope field through which I flow, if I drop a point right here, or a leaf right here, will be the function y equals plus or minus the square root of 2x squared plus 16. There's the particular solution. Okay, so over here we have an alternating current circuit. It's pretty much one of the most basic alternating current circuits, and in Physics 1 and 2, algebra-based AP class physics, we usually don't really do a lot with alternating current circuits because that's more of a calculus-based physics thing. Sometimes I have my class work with them a little bit because most people in my class have taken calculus. That's just the way we do it here. So this is a pretty basic circuit. I thought I'd just introduce you to some of the components of that circuit. When we work with circuits in physics, we're going to see these guys all over the place. This guy represents anything that resists electron flow. So this is a little resistor. There are actual components that, are in pretty much every piece of electronics imaginable that resist electron flow to make sure that not too much electrons flow through something and heat it up or melt it, you know what I mean? So there's all kinds of resistors in pretty much everything that's electrical, whether it's an alternating circuit that device is made of, or whether it's a direct current circuit, yeah? So these are super, super ultra common. We're going to see those all over the place. This guy we're not going to see as much because this is just in an alternating current circuit. In other words, something like the wall that has alternating current that changes directions. Since alternating current changes directions, that's where you really have to start using calculus to study. So we won't see too much of that in our first physics class. But this guy is called an inductor. Okay? And the H, the Greek omega, and the V, that's just the units on each one, right? So this is resistance, That is measured in ohms. So you might write that down in your notes. You might have seen that before. H, you know what? I haven't worked with inductors for so long that I've kind of forgot what H is. I think it's not. I forgot it. I can't remember. I haven't used it for so long. Anyway, V over here is for voltage. So this is like the guy that's producing the electricity to begin with. We'll think of it as like an alternating current generator of some sort. But that would just be like the wall or the power plant in, you know, an alternating current situation like in the wall. So this is the guy producing the voltage, right? That's 60 volts. Okay, and what do you guys think this is over here? It's pretty self-explanatory. It's a switch where we can turn the electrons off or we can let the electrons flow, whether we turn the switch on or off. So in this circuit, since it's an alternating current circuit, you have to use calculus because the current, the I, that's what the I represents here, the current flows backwards and forwards, so its rate of change is quite variable. Where do you see rate of change in this little equation? di dt, that says the rate of change of electrons per time, right? So that's kind of why we need calculus in this situation, because it's going to change over time because it alternates, yeah? So, for whatever reason, we're not going to study the physics today, but we've got an idea that there should be a changing current in there, right? This setup, for basic physics reasons, comes out to that differential equation. If you have 60 volts producing the voltage, if you have 12 ohms resisting it right here, and if you have an inductor trying to reverse things over here, I'm not going to talk about a lot about inductors today. This is the differential equation which represents that circuit. So at the beginning of time, before this is switched on, you have a pretty, I think, commonsensical initial condition, which is the current at the beginning of time is 0, right? That makes sense before you flip the switch. Once you flip the switch, things start to happen and your electricity situation flows forwards in time. So, can we solve this differential equation just by separating variables? I think we can. So can you guys help me separate? What do I need to move? Remember, that's just the initial condition. We need to get the i's on one side and we need to get the t's on the other, exactly. So I'm going to say, we can reduce this pretty easily to begin with, can't we? I can get rid of this pesky 4. How? I could divide by 4 everywhere, right? So if I divide 4, it'll just go away. This situation is a nice one. So I'll have that be that, divide 12 by 4, divide 60 by 4, and you get 15. Okay, can we get i's by themselves now? This one might be a little bit harder to separate. It originally looks like it's not going to be separable, but you can do it. I'm going to go like this. And now what can you do? Yeah, I did it that way. Multiply the dt over. Looks like there's 2 pieces and you're not going to get a separation, right? But you can think like that. And then do what?
Divide it.
And then divide this thing to the other side. So I'm going to have di divided by 15 minus 3i equals dt. That is indeed separated, even though it looked like it wasn't going to separate. And if you look at one of my future videos, it looked kind of first order linear right here. And in fact, I think it might satisfy that as well, but it's easier to separate if you can. Okay? So, now what are we going to do? We've got things separated. Integrate. Okey-doke. I think we'll need some space, so let's go over here. And we're going to have what? You guys help me with that integral? So we're going to have t plus a constant. Maybe I'll call it a temporary constant just in case on that side. And on this side, what am I going to have? What? Negative 1/3, the natural log of 15 minus 3i. You could, of course, write the u sub out and call this u down here and do it with the u substitution. That'll work as well, but I think this one's nice and zenable. You just got to watch out for that chain rule from the negative 3. So I compensated, or Claire compensated, by going negative 1/3. Okay, Can we solve this for I? We could just leave it implicitly. I think I'm going to try to make it explicit because I want to see what an alternating current looks like. You guys know what I mean? I'm going to solve for I so I can see what an actual alternating current looks like. That's an important thing for us when we're starting to think about physics. So let's go ahead and move that 1/3. So I'll say natural log of 15 minus 3I. And we'll go negative 3t, right? So multiply by negative 3 here, multiply by negative 3 here. So I'm going to call this temporary constant number 1. This one was just regular temporary constant. I'm just naming them different things just to keep track, okay? And then how do I get rid of natural log? E. So I'm going to go e to the stuff. And I'm going to say e to that stuff, just like we've seen in previous videos. Works like this, right? We use that special rule. And we'll just call this guy C. Or what did we call it before? Let's be consistent. We usually called that constant K. It really doesn't matter what you name your constants, but we want to match tradition. Just so we feel comfortable later on when we see things like this in physics. Okay, now what do? I want to move my 15. And finally I'll divide. 5 plus, oh, I should have called this temporary K, but see, I can go back up there and fix it so that I get a nice clean regular K right here. But don't let the naming fool you, right? Like I'm just naming things to be consistent, that things are different constants, right? So this is going to be K e to the negative 3t. So K temporary was K is K temporary divided by negative 3. Anything else? Could I have called this minus just to clarify there? It really doesn't matter, right? Because that's just a constant. So that's the general family of solutions for this kind of circuit that represents how the electricity flows or how the current flows. This current is I. We wanted to find the one for this specifically given that there's no current at the beginning of time, which makes sense. I don't know if anything else would make sense. Maybe there was already a current flowing, I don't know. But for us there wasn't, so we're going to say 0 equals 5 plus K e to the 0. So that's going to be negative 5 equals K times e to the 0 is 1. So K is equal to negative 5. So my particular solution to this differential equation will be 5 minus 5e to the negative 3t. That is the current that will flow through that circuit. Let's look at some situations where we want to predict what a growth or decay situation looks like. And that's going to be a very special and probably the most iconic differential equation. So, as it says, a plethora of applications involve some kind of rate of change, one variable being directly proportional to the amount of that variable, in other words, to that variable itself. This is the most common kind of changing relationship that we see in basic differential equations. And it's one that if you take a class in differential equations, your teacher may or may not spend a significant portion of that class hammering on this, depending on how good your class is. Mine wasn't so fantastic, so we spent an inordinate amount of time on this and I wanted to quit because I wanted to learn new math, and I almost quit, and luckily after that we finally learned some new kinds of differential equations. So a pretty important concept, even though sometimes it can be a little bit elementary, I think. So one type of rate of change that you should be pretty familiar with using variables we're used to is what if the rate of change of y with respect to time was proportional to the amount of y itself. We're used to k being usually our directly proportional letter, right? But you could call this anything. For instance, if you ever take physical chemistry in college, like if you majored in chemistry, if you wanted to be a pharmacist, you'll have to take physical chemistry, and you study how drugs relate to each other in chemical reactions over time, you're going to be working with these equations a lot. And they're probably not going to be the same variables, but it's going to be the same kinds of equations based on chemical reaction rates. Because a lot of chemical reactions, the rate of change of that reaction is proportional to how much you started with. That makes sense, doesn't it? Like how fast it changes has to do with how much sulfur you had at the beginning or something. So anything like that is this kind of math. So not too hard, this kind of math, though, luckily. So I said, in such cases, a productive family of solutions, it might not be the only one, maybe there's like one with trigonometry as well, but a productive family of solutions is simply y equals c e to the kt. Now the other day, when we did this one in class, we usually called this k and this was e to some number t, right? But this is the same thing we saw in class the other day. Do you recognize it? I hope you do. So if you're watching the video, or if you're having trouble with this idea, like where did this come from, just separate variables on this. This is like the easiest possible equation to separate variables on. I think we've already done it in my class. So if you don't believe that this is the solution from separation of that, go ahead and pause and confirm that now. But I think you guys could probably believe me. We've seen it twice already, have we not? So what we're going to do today is use that for some simple applications involving growth and decay. And this kind of goes back to Algebra 2. You've seen these problems before, but hopefully now you're thinking they're a little easier, you have a little firmer foundation. So for instance, here's one without context. The rate of change of y, and here's a new symbol for you. Mine looks like the Starship Enterprise from the old Star Trek, but this symbol means proportional. You might see people using it. I'm not particularly good at drawing proportional symbols. Mine always look like the Starship Enterprise. But it's pretty close. That symbol means the rate of change of y is proportional to y. So that's what I'm saying, is that in this problem we have this kind of situation. Yeah? So I also have some measurements. It says when time is 0, y is that much. And a little bit later, at time 2, y is that much. So we're supposed to find the value of y at time 3. So what we can do here, and I have my Algebra 2 students do this with no calculus, but I don't tell them why it works that way, right? We now should be able to understand why it works that way. If the rate of change of y is proportional to y, then we know differential equation-wise that dy dt is equal to some constant times y, right? This is really just a new way to think about some old concepts from Algebra 2, but it should strengthen you up on what those meant. So if that's the differential equation, we could of course spend some time separating it to solve, but we already know the solution, right? The solution is going to be y equals what? Constant e to another constant t. So I know this is going to happen just based on the type of differential equation this is. It's kind of like a fact that's useful to memorize. It's not really just a fact, though. It's a whole situation. Very important if you're going to go on and do something like chemistry. So, do we have an initial condition so we can take this general solution and make it fit our situation? Yes, we do. It's kind of like we have an initial condition of 0, 2. So let's apply that and see what happens. So we'll plug in and we'll get 2 equals c e to the k times 0, and k just kind of dies right there, right? So that says c times 1 equals 2, so that says c equals 2, correct? So now I can plug that in and start to find my particular solution, so I'll have y equals 2 e to the kt. But if I try to now go answer their question, I think I'm going to be stuck and out of luck because I have another constant. So if you have more than one constant in your general solution, you need more than one condition. This was the initial because it was at time 0. I need another condition, call it what you will. Do I have another condition? I do. That's exactly what this is, this 2, 4 condition, to find the particular solution. Does that make sense, guys? That's a little new. In partial differential equations and in other kinds of differential equations, sometimes a condition is like the beginning of time. Sometimes it's like you have a tube through which heat is flowing and you need to make sure that the edges of the tube don't get too hot, you know what I mean? So they need to be a certain temperature, so that would be like a boundary condition. That's the way things work in thermodynamics a lot, or heat physics. Anyway, pretty important if you're working in the petroleum industry, for instance. Those pipelines. Anyway, we don't have that. We've just got another condition right here, so we're going to plug it in. So we've got 4 equals 2e to the k times 2, and I think I can divide that over and get 2e to the 2k, and then you guys tell me how to solve for k. Remind me of my algebra. Natural log both sides. We'll have natural log of 2 equals natural log of e cancels out. So we'll have k equals the natural log of 2 divided by 2, which we can go to our calculator with and get a decimal for. But I'm not even going to do that. Why? Because this is exact. I think we're in calculus now. We can handle weird looking stuff. Oh. So let's go ahead and answer our question now. We know the particular solution is y equals 2 for the first constant, e to the that for the second constant, t. Yeah? If you don't like this, if it scares you, fine. Turn that into a decimal, but then you're going to have rounding and you'll have some error. I don't want that error. Okay, so now I need to find what the value of y is when t equals 3. I can just plug it straight in there. Can you guys use your calculator? I don't want to get my calculator going today if I can help it. 5.6. Are you sure? Because I know another way to think about these as well. I'm thinking about this as being like some kind of decay or growth, and I'm thinking like 2, it's going to have to be less in the future.
Yeah.
Oh, it is 5. I guess it depends on this. What is this guy? I guess I'll have to ask you guys. What is this? Is this a more or less than 1? It's going to depend on that. Natural log of 2 over 2. What is it?
0.3465.
0.3465?
Yep.
That's all? 465.
Well, 73590B.
Okay, so it's not negative, so I guess this is an exponential growth function, so it makes sense that from 2, the initial amount, we grow up to a higher number, like 5.6. What was this one, just to clarify?
4.656.
Okay. And we don't have units here, but this is like an amount. So an amount of whatever it is. Sulfur,
2E.
petroleum, I don't know. Let's look at one more problem. Let's suppose we have 10 grams of a radioactive element, like plutonium. Let's say it's decaying. And let's say these 10 grams were released in a nuclear accident, like the one at Chernobyl. You guys remember when Chernobyl happened? 80s, good. So it was in the 80s. I think it was 89. But anyway, so we have some plutonium that's been released. It's weapons grade, so it's the bad kind of element to be released into the atmosphere. Still something that Europe is dealing with today. So the question is, how long will it take that 10 grams to decay to 1 gram? This is a familiar question from Algebra 2, basically textbook. You're going to see lots of questions in this section like that. What I'll challenge you to do is make sure you're always thinking about, is the differential equation one that's where the rate of something is proportional to its amount? And if so, then you can apply that. I think this is a situation where that's true. So we're going to say the solution to this differential equation will be the familiar one we just used a second ago. So if that's true, we want to figure out how long it will take that to decay. So we need some conditions. So we had one condition. Did you guys pick up on it when I described it? We had the amount of grams of the substance at time 0. That was 10 grams. So that's the initial condition. I think we're going to need another condition because we have 2 constants to determine. How else might we get another condition? I don't think I said it. I think you have to determine like something about the specific substance and how long it takes to decay. That's called the half-life. Yeah? That's what a half-life really is. It's something that determines how long something lives or dies. In this case, how long it takes until it dies to half of its original amount. So you could look that up on the internet or in a table or glossary somewhere. But another condition that we're going to have is the half-life of plutonium is 24,100 years, this type of plutonium. So if its half-life is 24,100 years, how am I going to write that in a condition? What, comma, what?
Is that what our 24,000
That's the time until you have how much?
9.
Half-life.
5.
Sorry.
There we go. Right? That's what a half-life means. So now we've got 2 conditions. We can solve it, and we'll be able to answer any question they ask us. So let me find my blue marker, and I'm going to say 10 equals CE to the 0, because the 0 will kill the K. So that's 10 equals C times 1. So that's C equals 10. You'll notice in this kind of simple differential equation setup that the original amount is always going to be the thing that constant is. That's why that's the original amount. I just told you in the past with exponential functions that thing in front was the original amount. Hopefully now you should be seeing why it's the original amount. I think we've done it 2 or 3 times already. So we've got that. So we're going to say, okay, so now it's y equals 10e to the kt. My Algebra 2 students might even be able to do that and say, hey, put a 10 there. So now we're going to say, okay, now I need to plug in and find the other part. So I'm going to have 5 from the original 10 when time has transpired this far. So I'm going to go 1/2 by dividing the 10 on both sides equals e to the 24,000k. And of course I'm going to natural logarithm that. That will kill the e because the natural log of e is 1. And so k will be the natural log of 1/2 divided by 24,000, which is in other words the half-life. So there's the exact value of k. If you're getting scared by it, of course, it might be helpful to put it in your calculator. This is going to be a really small negative number, is it not? You guys want to confirm that? So I think this is a situation where it really does matter a lot if you keep this in exact form. So I'm going to keep it in exact form when I answer the question. I think the question was, how long to decay to 1 gram? So we know it's definitely going to take longer than what? Longer than 24,000 years. Maybe it'll be 90,000 years, something like that. But exponentials aren't like lines, right? So it's probably not going to be a perfectly symmetrical thing. But it's definitely longer than 24,000 years, probably a fair amount longer. So how do we find that? We say, okay, there's our function. Y equals 10 e to the that stuff times time. There's the particular solution. So I'm going to say, if I want 1 gram left, that is my y that I put here, and I can solve for time. So I think at the calculation or the algebra is the same exact thing as we did right there. So I'm going to divide and get 0.1 equals e to the stuff. And now I need to get rid of e, so I'm going to natural log it and say the natural log of 0.1 equals natural log over here kills this e, but this natural log is left. And remember what you're trying to solve for. I'm trying to solve for time. This is just one big ugly number that I left in exact form, so I'm just going to divide it to the other side, right? So I'm going to have t equals natural log of 0.1, whatever that is, divided by this number. Natural log of 1/2 divided by 24,100. So it might be wise to move this divided by 24,100 just to make our calculation easier in the calculator right there. And I can see what we get. And let's see how long it's going to be for this plutonium to go away. Oh, this calculator wants to die. Of course. Is it 80,000 something? Let's see.
Yeah, that's what I got.
That seems like a reasonable answer to me, right? Yeah, there we go. I wasn't very careful about my parentheses here, but I know what order of operations the calculator is following. So be careful with your order of operations when you do problems in this. So there you go. You're going to be using this traditional solution on a lot of problems. There'll be ones with charts where they give you different conditions in different ways, but don't make it hard on yourself. It's just Algebra 2 problems, basically, with a little bit of calculus background. I'll see you next time.